Okay, looks like I should begin. So, hello everybody and welcome to my TED Talk. So, I know what you guys are wondering. Who is this girl and has she ever solved the quadratic equation in her life? Yes, I have solved it, and I am Victoria, and I'm a scientist from Pixar. And today I will be talking to you about the magic of the cinema and the colorization of the old times. And as the title suggests, a touch of color or enhancing the magic of the past. Let's go. So how was colorization done? Well, in the antique ages, everything was pretty bad per se, because colorization used to be done by hand. So imagine you have this boy, and then you just had to color everything by stencils, by watercolors. You used fine brushes, you used your fingers. Imagine doing all of this by your fingers. It was a disastrous process. And this is an example of it. This is one of my favorite movies, A Trip to the Moon. It was published in 1902. The colorized version was found in 1993. And to actually colorize this, around 120 hardworking women had to colorize 113,000 frames manually. Guys, that's not easy to do by any probable means. So yeah, and also a couple of fun facts about this. You guys can see the Spanish flag. It is because it was sold to a Spanish distributor. However, everything was done in France. And also, you guys can see how vibrant everything is. Was it like that in real life or not? Kind of. I mean, the sense of fashion wasn't that off. People didn't wear things like this on usual basis. However, to actually make it visible in movies, you had to have vibrant colors. That is also the exact same reason why Monroe's lipstick was that shade of red, because any other color couldn't be visible through the camera. And then came stencil colorization, which cut the workload by half, sometimes by 3 times. And how come? Because you had the tape, you just could colorize one single tape, and then you can just move it over, copy it down to other stencils, and then you had a colorized image. So yeah, this was the antique ages and everything was disastrous. This movie came out. This movie is the movie of the man, the legend himself, Casanova. Also, one of my favorite Russian singers sang about him. That's also a fun fact. And yeah, this was also, that took a lot of time, and this came out in 1927. So around that time, color TV was invented. Around that time, colorization, like actual film colorization, started taking process. But if you guys remember, like Casablanca came out in 1942, and it was still in black and white. Monroe was shot in several films in the 1950s. They were still black and white, so colorization was still a problem. However, like everything was going to color TV. And we didn't encounter this problem till ages later, to when we already had like computers, we had signals and so forth. So the one with the past, yes, this is a Friends reference. I love that TV show. So as you guys can see, there are no pictures here because what they did was they messed the signals. So this is actually the first patented algorithm of colorization. And how did this one take place? So you had a frame, you still had to color it manually, and then for the next frame you could just detect the motion. How do you detect the motion? You just subtract the 2 images from each other. This is what the layers are for. So this radio stream, what it does, it is basically subtracts, and then it finds whatever has changed. When you find whatever has changed, based on that you will know what to colorize, what to change. And you just find the pixels, you just find the places that actually changed, and then fourth, you ended up giving new colors to the parts that changed. You assign the new colors, and then so forth. It's an iterative process. However, this did cut the workload by a lot, like really a lot, because the manual part got a lot less. And we can actually bring a new term here. We can bring the term specialist here. So who had to give this scheme something? Somebody who was a technological expert and somebody who knew coloring. Yeah, to be a specialist back in that ages, it was again disastrous. And finally, we have the day of computers, digital colorization, the first actual algorithm that came on to colorization. So you guys can see this kiddo is smeared all over the place with colors, and the one on the left is the actual colorized image. We used the algorithm of colorization using optimization, and what this did, it basically found similar segments, and then it made sure that the similar segments were colored the same way. As the title suggests, neighbors tend to act alike. So what we did is we minimized the loss. The GU is the loss function. The UR is the color of the pixel, and we made sure that the color of this pixel was alike the color of the neighborhood of the pixels. WR is the weight based on which the neighborhood was calculated, and it could be a Gaussian function, it could be a mean variance-based function. The mean variance-based function actually performed really well because it ended up taking into account edges and intensity drops. So that's how you got the colorization. For this case, the user, the specialist, only needed to be somebody who knew design or somebody who had basic intuition of how the image should actually look like. So this is 2004, and basically nothing changed till 2015. This paper came out in 2015. It's called Digital Colorization. I cheated here a bit because I showed an image of colorization instead of recolorization instead of colorization. Recolorization is when you already have an image that has colors and then you try to change the color of it. Colorization is when you don't have anything. You just have a grayscale image and then you want to add colors upon it. However, the tasks can be brought one upon to another. If you have this image of the green leaves, you can just make it grayscale and try to colorize it. Or if you have a grayscale image, it has some fragments of colors because like the tapes used to leak. So you have some sort of information about the natural segments. And this algorithm, it was published by Adobe, and it used to be pretty fast. And that's the only advantage it had. You still needed a user. The user still had to tweak everything, and yeah, you couldn't completely eliminate the user. And as you guys know, our main goal in artificial intelligence is to make everything automated and to eliminate the user. So, and this is the charming present. Finally, we have data. So what does data do? It helps us generalize everything. It just helps us generalize. This is an image of a lady that it was taken in 1936. If I'm not mistaken, she's a Pakistani refugee, though it would be good if you guys checked it. I have the sources in the end. So I'm not sure if you guys can see it, but we basically have like little spots everywhere, colored spots. Those spots are what we call priors, and based on the priors, you could recolorize the image. So you guys might be thinking, we still have a user, how is this any different? Well, we also have a network, a convolutional neural network that helps us do generalizations. Or like you guys can see in this example, the skin colors isn't messed up. You can colorize a single image in multiple ways because there is no right way of colorization. You can have it blue, you can have her t-shirt yellow. There was also an example of a green t-shirt. Everything can be messed upon because there is no one-to-one mapping. Why? Because you have a 3-channeled image. You have an RGB channeled image. You make it grayscale. You use 2 channels, you lose information. So you cannot bring back the information in a single way. And here's the architecture of the SADnet, the priors. You guys might think this is complicated. No, it's not. This is actually pretty simple. What we have here is an encoder-decoder system. The user gives us the local hints. The local hints are basically the colors. Like you guys just see the spots here. These spots are the local hints. Also, there are global hints. The global hints are generated. The global hints depends basically on which type of framework you specifically want to use. And based on the local hints, so you give really few spots. This local hints network just generalizes and makes a huge color distribution. And then based on that color distribution, you can apply it to the grayscale image. And that's how you get the output image. This is one of my favorite algorithms, but it has cons, and I have to state them. One of the cons is, so this is a really beautiful picture taken in New York, 1945, a raw display of human emotion. This is a spontaneous picture. It was after the war. And I'm not sure if you guys can see it, but this has dots all over the place. And if somebody gave me this image and told me to colorize it, I would just do the lady, maybe the buildings, and I would call it a day. I wouldn't do like a full-on colorization, and the more priors you have, the better results you'll get. So for the user, it will end up getting pretty exhausting. And then you have the image of the Hulk. It's still user-dependent, meaning it's not what we call idiot-proof. If the user wants to make everything green, then you'll end up getting a green human. That's not really good because humans don't tend to be green. I mean, for the memes, sure, you can have it, but as a realistic colorization algorithm, this has cons. And the next algorithm is exemplar based. Oh, I forgot to say the previous algorithm came out in 2017. That would be so fun though. And this one came out a year later, exemplar based colorization. In this case, the only thing the user needs to do is the user needs to choose an image. And as you guys can see, based on the image, the colorization will be performed. So in the upper image, we have an image of the lady and the man is recolored. In the lower image, we have an image of the car, and you guys might be thinking, no matching semantics. Well, yeah, that's the magic of data and generalization. It just knows that if it has the semantics of the human and the specific tone, it should give it the specific colors. So what this does is that you give it a, yeah, it's actually a little bit better with lower down. No, lower down. Yes. Okay, you gotta have it your way. Okay, in the end, we can just turn off the lights and see the pictures again. I love the pictures too, trust me. So we have here a photo of the car, and it basically just tries to find matching semantics, magic segments, and based on that, it colorizes the human. So the job of the user is now significantly less. The only thing you need to do is just find a good reference picture, and I'm sure you guys can do that. So in this case, each and every one of us can be the user. And this is how this works. Again, something that seems complicated, but it's actually really simple. When you have the two images, you need to make sure that they are aligned. So you align them using some sort of an algorithm. It doesn't really matter what. And after alignment, you need to find the similarities between those two images. You find the similarities thanks to the similarity subnet. And after the similarity subnet, you give this information to the colorization subnet, which colorizes your image. We have as inputs the grayscale of the image that needs to be colorized. We have as inputs the target image, thanks to which everything will be colorized. And as an output, we have the beautiful pictures. Is the next slide? No. We have the beautiful pictures, as we can see. And one more thing that I should mention is that everything is done in the LAB space. LAB space is a derivative of color spaces, and it's really good to do it in LAB because the grayscale usually matches to some degree with the L channel. Not like specifically, but both of them are used to show semantics. And thanks to the semantics that we end up displaying, we can actually just predict only the A and B channels. So in the first case, we had the grayscale image, you had to predict 3 channels, a lot of work. In the second case, the network can do just generalizations and you only need to predict 2 channels. So yeah, you need to predict less data, that's really good for the network, less room for error. And finally, the utopic future and what can actually happen in the future. So this paper isn't actually from the future. If I could do that, I would really like to know how the football match ends tomorrow. But no, this is a paper actually came out in this year, in March. And it uses a transformer. So what this does, you don't need a user in this case at all. Why are transformers really good? Transformers are really good because they have really high fidelity, and thanks to the really high fidelity, they can generate a lot of variations of the same data. So we have this beetle, and you can color it in lots of ways, and most of the ways the humans themselves wouldn't think about it, but thanks to the data, the transformer can end up making generalizations. Like in the first case, I would never give the guy a red costume, like never. But it does work on him, I will tell you guys that. But when a human is given this task, they would probably not do that. And after running this network, a user study was performed. So we have the ground truth data, and we have the data that the transformer generated. The ground truth data is the original image which we made grayscale. So the user had to compare the ground truth versus the things the transformer generated, and then 60% of the cases they actually preferred the augmented transformer output versus the ground truth, meaning the possibilities really are endless, and we might not be able to really restore the past, but we can sure give it a hell of a spin. And these are the sources. If you guys want to like read about something, you guys can just ping me and I will send you the sources. And this is the one with the questions. So, any questions? Damn, did I present that well? No.
Can you go to the slide, I guess it was number 3, all the way to the beginning? Yeah, go.
That's why I needed pagination.
No, not this one. Go. This one. Okay, so you said, if I remember correctly, that 20 women had to...
120.
120, yeah. So I'm deeply disgusted by the fact that no males actually participated in the process. So don't you think that it would be much better if we had 60 males and 60 females doing that job?
I am so glad you came to my presentations. Yes, of course. I mean,
I think we should stand that for that position in the future. So make sure that if that particular image would come up for recordization task, we do it equally.
yes, I will certainly state that we need the equal amount. However, this is a lady's job, so I don't think a man with pride would be able to do it.
Yeah, we should change it.
Yes.
That was a comment to what you said.
Okay, any more questions?
I have a question. Can you use like flat colors for colorization? Like you select some colors that you want to use in MS Paint and then you use that as a reference?
Yeah, you actually can. For example, okay, so in this case, you can actually do that because you have this lady, we have an algorithm in ML which is called k-means or clusterization. So during the semantics matching, it just tries to find the matching semantics, but you can also perform histogram transfer. Histogram transfer is almost the same thing that you stated, however, we know which color should be how much. But yes, you can use this, you can also, in this case, you can just slap any color you want and you will end up getting the result you want. More questions? Damn, I'm a good presenter if nobody has questions. Thank you. Oh guys, we're not done yet. If no more questions, then this is the one with the vacancies. In PixArt, we have a bunch of, did I mention that I'm from PixArt? Okay, in PixArt, we have a lot of, oh yeah, I didn't see that one.
Oh, wow.
Yes, we have vacancies for senior vision engineers, senior machine learning engineers, senior full stack developers for the engineering team. They're the one who implement the things we write. And yes, we are done.